Moore's law successfully forced the reduction of the channel length below 50 nanometers. This aggressive reduction dramatically increased the influence of the drain voltage on the channel potential barrier. This physical effect is defined as Drain-Induced Barrier Lowering, or DIB. DIB causes the transistor to conduct current even when the gate voltage is zero, defining the off state. Simultaneously, the gate oxide thickness could not scale proportionally due to fundamental quantum tunneling limits. This disproportionate scaling resulted in poor electrostatic control over the channel region. The resulting loss of control significantly increased the static power consumption, known as leakage current. This catastrophic increase in leakage current effectively halted further effective scaling of the traditional planar MOSFET architecture. Transistor efficiency is quantified by the subthreshold swing, measured in millivolts per decade. The subthreshold swing defines the required change in gate voltage necessary to increase the drain current by exactly one order of magnitude. The theoretical ideal subthreshold swing is 60 millivolts per decade at room temperature. This limit is dictated by the fundamental Boltzmann distribution governing carrier injection over the potential barrier. High drain-induced barrier lowering significantly degrades the subthreshold swing, pushing it far above the 60 millivolts per decade limit. An increased subthreshold swing means the transistor cannot fully turn off, resulting in a high off-state leakage current, or I-off. This leakage current is dominated by diffusion current in the subthreshold region. This diffusion current wastes substantial power even when the circuit is completely idle. To maintain the ideal 60 millivolts per decade subthreshold swing, the gate must exert complete electrostatic control over the entire channel volume. In traditional planar devices, the gate controls the channel only from the top surface. As the channel length shrinks, the source and drain terminals gain increasing control over the channel center, a failure mode known as punch-through. The engineering solution requires wrapping the gate around the channel structure. This maximizes the coupling capacitance between the gate and the channel. It also minimizes the physical distance between the gate electrode and the channel volume. This structural change fundamentally transitions the device operation from a two-dimensional surface control mechanism to a three-dimensional volume control mechanism. The Fin Field-Effect Transistor, or FinFET, replaces the wide planar channel with a vertical silicon fin structure. The gate electrode is engineered to wrap around three sides of this fin, the top surface and both vertical sidewalls. This configuration inherently defines the FinFET as a triple-gate device. Fabrication begins by etching the silicon substrate to precisely define the fins using advanced lithography techniques. High-K metal gate technology is then deposited conformally around the entire fin structure. The effective channel width is quantized and determined by twice the fin height plus the top width multiplied by the number of fins. Current flow is primarily conducted along the vertical sidewalls of the fin. The FinFET's multi-gate structure ensures that the electric field originating from the gate fully depletes the entire volume of the thin silicon fin. This full depletion mechanism eliminates the bulk region, which is where parasitic leakage paths typically form in planar devices. By controlling the channel from multiple sides simultaneously, the FinFET drastically suppresses drain-induced barrier lowering. This improved electrostatic control successfully restores the subthreshold swing close to the theoretical 60 millivolts per decade limit. The result is a significantly lower off-state leakage current, I-off, and a substantially higher on-state current, I-on, for the same power budget. This structural improvement dramatically enhances the critical I-on to I-off ratio. FinFETs enabled the semiconductor industry to successfully scale below the 22 nanometer node, initiating mass production around 2011. Compared directly to planar transistors, FinFETs typically reduce static power consumption by 50% while simultaneously increasing switching speed by 30%. The discrete nature of the fins allows for precise control over the threshold voltage, V threshold, by adjusting the fin height and the doping profile. FinFETs are now essential components for high-performance computing and mobile processors where power efficiency is paramount. However, the quantized nature of the fin width complicates analog circuit design compared to the continuously variable channel widths available in planar devices. As semiconductor scaling approaches the 3 nanometer node, the required fin width becomes excessively narrow, leading to increased resistance and manufacturing variability. The next evolutionary step is the gate all-around field effect transistor, or GAA FET, which completely encircles the channel structure. Gate all-around structures typically utilize horizontal silicon nanowires or stacked nanosheets. Nanosheets offer superior electrostatic control compared to FinFETs because the gate controls the channel from all 4 sides simultaneously. This structure further minimizes drain-induced barrier lowering and allows for a better current drive per footprint area. Gate all-around technology is critical for extending Moore's law into the sub-2 nanometer regime, successfully maintaining necessary power efficiency and performance gains. As semiconductor scaling approaches the 3 nanometer node, the required fin width becomes excessively narrow, leading to increased resistance and manufacturing variability. The next evolutionary step is the gate all-around field effect transistor, or GAA FET, which completely encircles the channel structure. Gate all-around structures typically utilize horizontal silicon nanowires or stacked nanosheets. Nanosheets offer superior electrostatic control compared to FinFETs because the gate controls the channel from all 4 sides simultaneously. This structure further minimizes drain-induced barrier lowering and allows for a better current drive per footprint area. Gate all-around technology is critical for extending Moore's law into the sub-2 nanometer regime, successfully maintaining necessary power efficiency and performance gains.